Hello Year 10 and welcome to my first lesson with you guys doing triple chemistry. Now Miss Dobbs is going to be giving you an introduction either on a separate PowerPoint or typed, so I'm just going to crack on and get on with this topic. I believe you've already covered the parts of crude oil, fractional distillation, and I'm not sure if you've done combustion or not, but either way it doesn't fall under the scope of this lesson. So today we're going to be looking at the structures within crude oil and the hydrocarbon families that are present both in crude oil and after we have done a process called cracking, which you'll also cover in a future lesson. Now, I occasionally, if I get overexcited about something, theme a PowerPoint with some silliness. So this one is themed based on a computer game, which some of you may recognize. Okay, so we are looking at alkanes, and actually we're going to look at alkenes as well. So this is a recap that I'm sure is not going to tax your imagination one bit. What do all of the following things have in common? Polythene bag, a road, a pen, a Lego Wall-E, a PVC catsuit, a Ferrari, some Vaseline, an aeroplane, and one of my, I probably ought to delete that actually, one of my ex-students' jumpers. It's the jumper or trousers I'm looking at there specifically. Bunsen burner, and a camping stove. Well, hopefully you all got that those are all made from or use parts of crude oil. So they're all made of them except for the aircraft, which of course is being fueled by kerosene, and the Ferrari, which is probably being fueled by a high-octane petrol mix. So all of the others either contain, in the case of the camping gas stove, some butane probably. The Bunsen burner is burning methane. Vaseline is made out of one of the longer hydrocarbon chains. Naphtha, I think, potentially. And good old Robert there is wearing a jumper made out of polyester, just like the plastic bag, or polyethylene, like the plastic bag. That probably is a polyester jumper, but either way, it is, as far as we're concerned today, a hydrocarbon polymer. Moving on. So, what you have probably, or what you haven't covered yet, is the structure and naming of the molecules that make up the hydrocarbons you've been looking at. So hopefully you've covered the name hydrocarbon as being a substance made out of only atoms of hydrogen and carbon. But actually at GCSE chemistry we need to be able to draw and name at least 10, well, at least 9 hydrocarbon molecules. Your exam board specification is a little bit hazy on this point, and I'll explain as we get to doing that in a second why I'm teaching you what could be argued is one more thing than you need to know. So here is an introduction to the alkanes. Now the alkanes are our basic, most simple form of hydrocarbon. They consist of little carbon atoms bonded to each other in a chain, and then connected off the side are hydrogen atoms. I appreciate that my doodling hasn't really added anything to that picture at all, apart from to make it look worse, but you can see on the side here we've got a carbon atom with hydrogens bonded to it. Now, what you probably do know from this representation here is that these sticks are a chemistry way of representing a covalent bond, and you can see a pattern emerging with these hydrocarbons. One carbon has 4 hydrogens. 2 carbons, I don't have 8 hydrocarbons. Due to some rules we'll cover in a second, they increase in a way of adding CH2 each time. You always add this repeating unit, CH2, and that fundamentally is the property that makes an alkane chain, is that repeating CH2 unit. This slightly complicated bit is I've got to put extra hydrogens on the end. So, these are our alkane molecules. These are the first 3. So, let's have a look at what hydrocarbons are. So first off, that's a 2-mark GCSE exam question. What is a hydrocarbon? And please, you're all brilliant students, please remember it's a 2-mark question. There is 1 mark for telling us the blatantly obvious, they're made of hydrogen and carbon. The other mark is for saying only. And I kid you not, 1 mark is for writing the word only. It will be emboldened in the exam in the mark scheme, and you will not get that 2nd mark without using that 1 word. It's one of those. So we've already discussed those sticks as drawn in my, and this is called the display formula. We call where you show all the atoms and bonds, we call that a display formula. So that is the display formula for propane, because I can see each bond and I can see each atom. And it's not showing me the three-dimensional structure, it's just showing me a nice 2D representation, so it's easy to draw, and it shows as much detail as we're going to need at GCSE. So those sticks between them, as we said, that represents a covalent bond. And of course, hopefully you remember from the beginning of year 9 and year 10 that a covalent bond is a shared pair of electrons. One single covalent bond is usually, but not always, made up with an electron from hydrogen and an electron from the carbon put together into the bond to make a pair. Let's get rid of the other two so I'm not left with 4 electrons there. That is a covalent bond. You don't represent them like that in the diagram normally. That's just to show what that stick represents. Okay, so there are some rules that govern drawing alkanes. Actually, this really should say alkanes, because the alkanes are this group of the most simple possible hydrocarbon. They are saturated. We'll look what that word means a little bit later on. So first off, in fact, no, I'll just recant that. These rules apply to everything. Every carbon atom always forms 4 covalent bonds. Let's count them, because that's sometimes a little bit tricky for people to see and appreciate. We'll look about this carbon here. 1 bond, 2 bond, 3 bond, 4 bond. This carbon here, actually let's use a different colour. Let's use some blue. That carbon forms 1 bond, 2 bond, 3 bond, and is also part of this bond, so 4 bonds. So you don't just, this carbon doesn't own a bond, it just forms a bond that then is also bonded by another thing. So each carbon atom always forms 4 covalent bonds. Secondly, every hydrogen atom can only form 1 covalent bond. Now there are slightly odd circumstances you'll meet in further chemistry when you go on to do A-level where things form different numbers of bonds for special, very short-lived reasons. As far as GCSE is concerned, and really A-level most of the time, and degree level because it's how reality operates, these are hard and fast rules, so just learn. If you have a carbon atom, it's got 4 bonds, don't deviate. And if you have a hydrogen atom, it has 1 bond, don't deviate. Okay, so 1 bond for hydrogen, 4 bonds for carbon. Let's just check. Let's do a hydrogen in green. Here's a hydrogen. And it has 1 bond. Oops, slight pen malfunction there. Moving on. Okay, so if I want to increase the length of this chain, every time I add a carbon atom, I'm going to be adding 2 hydrogens in order to maintain that rule. Now, some of you are probably thinking extension-y thoughts about, well, hang on a second, can't I put carbons into branches and have, rather than a hydrogen here, have a carbon here, and then go and do other things? And yes, you can, but do that at A-level, please. GCSE, we're just going to do 1 long straight chain of carbons in a row and not worry about branches at all. Thank you. Save that for doing exciting things at A-level. So, we're not going to be branching, we're just going to have straight chains, and each time I add a carbon, I add 2 hydrogens. Interestingly, even if I do branch, this rule does still apply, and I'll let you play around at your own leisure to see why that rule holds true, even if you start adding them in silly places. Okay, so we've talked about hydrocarbons in general. Let's talk about alkanes and their general formula. So what do I mean by general formula? Well, methane, our first alkane, is CH4. Ethane, our second alkane, is C2H6. And those of you who've noticed there's a pattern emerging, isn't there? And it's that addition of 1 carbon, 2 hydrogens. And because there's a linear addition as we go up, as we go along as we go through a series, that means that series can have an equation that gives you a value for a value of n. So if I know how many carbons I've got, I can tell you the formula perfectly. Let's have a look. So first off, there are always at least twice as many hydrogen atoms as there are carbon atoms, in alkanes, that is. And the at least is because each carbon in the chain, so not at the ends, has got a hydrogen above and below it. So we're going to have 2 times the number of hydrogen atoms we have carbons minimum. But also, at the end of the chain, there is a hydrogen at each end to give that carbon at the end its 4th bond. So in addition to the 2 carbons per hydrogen, no, 2 hydrogens per carbon, there is also an additional 2 hydrogens just at each end of the chain. That means that the general formula for any alkane is whatever the number of carbons is, the number of hydrogens will be 2 times that number plus 2. Because you've got the carbon, 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 carbon. Then here's the double the number of hydrogens. So I've put all the way along, oh no word, drawing H's with a mouse is hard. Well, this is a thing I've not done before. Sorry if they look a little bit like iodines or just something else. So there we have a not quite finished alkane with 4 carbons and 8 hydrogens. But this carbon, oops, that's too dark for you to see. Let's make it purple. This carbon and this carbon only have 3 bonds. So I check that and go, okay, so I've done the 2n, so where's the plus 2? Well, there's another 2 hydrogens to make it 2n plus 2. So I now have 4 carbons and 10 hydrogens, which is 4 times 2, 8, plus 2, 10. So CnH2n plus 2 is how you find the formula for any hydrocarbon. If you want to have a quick check, could you have a think about and see if you can work out the formulae for a ridiculous, well, it's not ridiculous, it's a perfectly valid hydrocarbon with 20 carbons. Have a think, 30 seconds, or pause, and I'll tell you the answer in 3, 2, 1. Okay, so I said 20 carbon atoms, so 2n, 20 is 40, plus 2, 42. The formula of a hydrocarbon with 20 carbons would be C20H42. Moving on. Right, so we need to know not only roughly what they look like, but you have to be able to specifically draw any of the first 4 alkanes. And you have to be able to name them. And you have to be able to do that from a display formula or their molecular formula, which is the little letters and numbers formula, and the display is where you draw them out with the sticks, or their name. So you must be able to, in fact, you should be able to draw them just from being told how many carbons there are and nothing else about them. So you need to be able to recall these well, or learn the patterns very well, so that you can always draw the first 4 and name them. Now you'll notice my slide says the first 5. That is for a very good reason. Your specification is sneaky. It says you must be able to name and draw the first 4 alkanes. But later on it also says the same about the first 4 alkenes. And for annoying reasons we'll come to later, they don't match up. So actually there's no reason whatsoever why you shouldn't also learn the 5th alkane, and that'll help you with the alkenes too. So I'm throwing in an extra 1 here, although not on this, well, I am on this slide. So the naming of these chemicals is very much like Lego. Their names are made of little blocks. So methane is the name of the first one. That's the one with 1 carbon and 4 hydrogens. Now it sounds like it's complete gibberish, but actually there's a bit of sense in here. Let's have a look. The meth, that basically just means 1. I can't remember if it's Greek or Latin derived. I think it's Greek derived, but I don't know. Please look that up for me. That would be amazing, because then I can say it in lessons properly. Methane. So meth, essentially, in this context, means 1, and it refers to 1 carbon. And so every, not just hydrocarbon, but every organic compound you encounter where there's a meth bit is referring to either all of it or part of it that has 1 carbon. And yes, I know you're all going to go and tell me about names that begin with meth now, because you're students. But yes, the name means that there are a CH3 group somewhere on that molecule. Okay, the ane bit tells it is an alkane, and that means we know that it's got only single bonds, and it's got the general formula of CnH2n plus 2. So this Lego name is how many carbons, what kind of hydrocarbon. Our next one, ethane. Eth is the way of saying 2 in organic chemistry, and again, ane, so it's an alkane. Propane, prop, the number for 3 carbons. So there's 1, there's 2, there's 3 carbons, and again, ane just means an alkane. But, which is not how you pronounce it. Butane. I know it's spelled but, we call it bute. Those good reasons. And, though what they are escape me. 5, which is the one you officially don't have to know, but it would be very silly not to learn, is pentane. So pentane is the 5th carbon, and again, the ane means it's a hydrocarbon. Now, I am personally well aware that just randomly learning meth, eth, prop, and bute as a new way of counting and pent is a bit of a pain in the neck, so in my infinite wisdom I've copied somebody else's mnemonic. And I've always used this mnemonic because it's nicely silly but quite memorable. Monkeys eat peanut butter. And of course the only problem with this mnemonic is it doesn't really accommodate pentane very well, and it's totally worth learning pentane, so I choose a word of my choice, and often I always tell my year 11 to choose a word of their choice that is memorable, so that they'll hopefully remember it's not propane but pentane. And I have to be honest, they don't always come up with words that I would deem entirely appropriate. So I'm not going to share their suggestions here, but monkeys eat peanut butter, I suggest persistently, or philosophically, or practically. Although that doesn't work as a sentence very well. Monkeys eat peanut butter practically is not very good. Monkeys eat peanut butter persistently, that'll do. Or a word of your choice. Whatever it is, learn it, please. Methane, ethane, propane, butane. Methane, ethane, propane, butane. Pentane. And remember that fifth one also begins with a P to confuse things. Okay, so what are the alkanes like? Well, you kind of know what they're like already because you've done the crude oil introduction, so you know the main uses, the main key things. The first thing you have to say about alkanes is that they are combustible. They are very, very importantly used in combustion. Now, apart from that, interestingly enough, they are pretty unreactive. So whilst they're very good at burning, they are very, very bad at most other chemistry. And that's kind of interesting because they're actually very good at burning. So there's a lot of energy stored, but the way the energy is stored is very, very stable. So it actually is quite difficult for them to do other chemical reactions. This is a good thing because it means we've got a very, very stable form of energy we can cart around in, say, petrol tanks, that when you put a small spark to it, suddenly gives you a huge amount of energy, and we've built our civilization on it. Hopefully we'll stop doing that soon enough before we destroy everything. Now, we need to look at the details of that a little bit. But they're not completely unreactive as well. It's worth saying that there are things you can do with them, particularly involving ultraviolet light, that will make them do chemical reactions. But fundamentally, they're pretty inert, except for combustion, which is their key reaction as far as, well, most of society is concerned. Now, because of this combustion reaction, they burn well, but they burn well as gases. They do not burn as liquids. In fact, very few things do burn as a liquid because burning is an interaction with oxygen, and oxygen is a gas. So in order for oxygen and a fuel to interact, they need to both be in the same phase to collide and have all those lovely collisionary reactions that make chemistry happen. So as gases, they burn well, but their chain length controls this because it controls their volatility. And that is how inclined they are to become gases. So the small molecules, like methane, evaporates very easily and so burns very easily. Whereas, let's think about, I don't know, diesel. I think 18 might be a relatively realistic length for a diesel molecule. I'd have to check that. Feel free to do so. That is very disinclined to evaporate. In fact, it's pretty disinclined to even flow. It's quite viscous if you put it into a boiling tube and stir it. It looks like vegetable oil almost. And that longer chain means it's very, very, very reluctant to evaporate. And because it doesn't evaporate easily, it will not burn easily. In fact, it's an interesting thing to try and do. Obviously, when I say to try and do, I don't mean all of you go to a petrol station, buy some diesel and set fire to it, because that would be crazy. But at some point in the future in a lab, hopefully I or Madam may already have shown you that if you take a sample of diesel and try and light it with a match, it will just ignore you completely. You need to heat up the surface it's on, generally with a blue flame of Bunsen burner, and then heat it directly itself to persuade this to light. Sorry if you can hear Just Work and small people in the background. I've got children about, of course. So, longer chain means less volatility, less inclination to evaporate, and therefore less flammability. And also that chain length, because this is basically longer chains mean they stick to each other better, they have stronger intermolecular forces. That means that not only do they not evaporate so well, but they're also stickier, they're more viscous. And of course that links back to fractional distillation, so longer chains have higher melting and boiling points, and so they evaporate at higher temperatures and are collected lower down the fractionating column. Longer chain alkenes are also, we've said this, less volatile, so they're less flammable and more viscous. That's the key link. So that intermolecular force property, the bigger chains, control the flammability, volatility, and viscosity. And those are the properties you really need to know about. It's also worth mentioning when you get to do combustion that a longer chain also doesn't burn as cleanly. You need lots more oxygen to be able to burn bigger chains to get carbon dioxide and water in an efficient manner. And so the bigger chains are much more prone to burn by incomplete combustion. But that's another lesson. Okay, so let's have a look at these saturates versus unsaturates, because we need to move on from the alkanes and meet the alkenes. So saturated are what we've looked at already. These are the alkanes. They are the simplest possible hydrocarbon. And they are saturated because, and I always like to say this, the word saturated, what does it mean? Well, if you imagine I've just used some kind of magic hand and picked you up and dunked you into a swimming pool and taken you out of that swimming pool, you are now saturated in water. There's no real way you could get any wetter. There is the maximum amount of moisture on your person. So in that case, you would be saturated in terms of water. An alkane is saturated in terms of hydrogen. It has got the most hydrogen stuck on it that's possible for that carbon skeleton to hold. Every single carbon is bonded singly, and therefore all their other bonds are bonded to hydrogen. Now, they of course have the general formula CnH2n plus 2, which is the largest number possible for any given number of carbons of hydrogens. Now, the fact that I've said saturated versus unsaturated should hopefully suggest that there are, of course, compounds that are not saturated, and these are the alkenes. We call them unsaturated because they have too little hydrogen. Can you see here? This feature is called a double bond, and it's very, very important chemically. That double bond is two bonds between a carbon atom rather than just one. And that means that both of these carbons have sacrificed a theoretical hydrogen that would have been here in order to have a double connection to each other. So that is no longer in a position where it has the most hydrogen possible. It is now unsaturated because of that double bond. Sorry about child in the background. So these are called alkenes, and you'll notice that in general in science GCSE spellings are not that important. Close phonetic is allowed. This is one case where it's absolutely not true. Getting that one letter wrong from alkanes to alkenes will cost you any mark you are talking about if it's important which you're talking about. And if you're using the word alkane or alkene, it's going to be important which one you're talking about. So make sure you get that spelling right, says Mr. Lund, the worst speller in the history. Okay, so we call them alkenes because of that double bond. So there we are, that's a paragraph summarising the existence of the double bond we've talked about at length. And this in turn means that they don't have that extra hydrogen on the end of the chain. And so their formula is actually simpler. They're not CnH2n plus 2, they're just CnH2n. Because you've lost those two hydrogens, you don't have that extra 2, and so whatever you have, however many carbons you have double that number of hydrogens. So my question earlier, what would an alkane of 20 carbon atoms be, is easier with an alkene, very slightly. So a 20 carbon alkene has, pause if you want to work it out, 40 hydrogens, because 20 times 2 is 40. So 20 carbon chain hydrocarbon, an alkene, would be C20H40. Moving on. So here are some nice little pictures of them, and once again we have to be able to name them. Now this is where it gets a little bit interesting, because your specification says you must know the first 4 alkenes, which you might think has a nice mirror, a nice parallel to the first 4 alkanes. But there's a problem. Can I have a 1 carbon alkene? Let's have a think. Well, what does an alkene have to have? It has to have a double bond to another carbon. Well, I can't have a double bond to another hydrogen because that breaks one of the rules. Hydrogens only form 1 bond, so that's out. So I can't actually have a carbon that has 4 bonds and a double bond to anything else because bonding to itself is not a thing. So I actually cannot have an alkene with only one carbon. That is not permitted to exist. It just can't be. So, the first one, which would be called methene if it existed, cannot exist. So the first one we're going to look at is, of course, ethene. And there it is, with its 2 carbons and its 4 hydrogens with a double bond. Now, from this point onwards, the monkeys eat peanut butter works absolutely fine. You've just got to remember that there's no monkey when you're doing alkenes. So there's no methene. There is an ethene. So we've got eat, and then we've got peanut, which is propene. And again, prop for 3 and ene for having a double bond. So monkeys, nope. Eat, ethene. Peanut, propene. Butter, butene. And of course, now we've got the 4 carbons. That's not our 4th alkene. So we have actually got to learn pentene this time. So 5. And this is why I say you may as well learn pentane, because if you just learn methane, ethane, propane, butane, pentane, then ethene, propene, butene, pentene is much easier to recall. Just skip methane, because of course, nope. I'm just going to scribble that out a bit more because it makes me feel better. Okay, sorry about Whingy Child. He's generally fairly happy, just not right now. Okay, so ethene, propene, butene, and pentene are alkenes, and you have to be able to name and draw any of those. Hopefully one or two of you are thinking, well, hang on a second, where do I put the double bond? Because I've drawn it at the end in each case here. It's a little bit hard to see on pentene there because it's getting a bit zoomed out. But they're all double bonds here. And, well, fundamentally, it doesn't actually matter at GCSE. And trust me when I say chemists can name to say specifically where that double bond is. Let's say it's not there. Let's say it's there instead. There is a way of naming to say my double bond is actually on the 3rd or 4th carbon, or between the 3rd and 4th carbon, or between the 4th and 5th carbon, or between the 1st and 2nd carbon. It is not a GCSE thing to be able to do. So come A level, yes, you'll have to be able to tell me exactly where in the molecule the double bond is, and you could draw it anywhere you like. And Googling pentene, you'll see there are a variety of, well, there's there, or there's there, are places you can put it, because there is just the same as there, because it's the mirror image, and there is just the same as there, because it's the mirror image. So there are 2 places you can put in pentene, and 2 places you can put in butene. And you're not wrong putting it in any of those places, as long as you follow the rules about how many hydrogens carbons have. Now this is the bit where I would now start drawing them on the whiteboard in front of you and making you have a go as well. And I'll make you do that as an exercise. But the thing to remember, this carbon here is the one you'll get wrong. If you make mistakes drawing alkenes, it's the carbon next to the one on the end. And I suggest you draw the double bond next to the carbon on the end for 2 reasons. 1, hopefully you'll remember there's only 2 hydrogens off it, because 1, 2, 3, 4 bonds. And then look at this one. This is the tricky one. You've got a bond here and a bond here, so that's 2 bonds. You've got a bond here, 3 bonds. You've got a bond here, 4 bonds. It looks like there should be a hydrogen here. There isn't. Don't draw it, or you give that carbon 5 bonds. That is the most common error drawing alkenes, is adding an extra hydrogen under here. And it's the thing you're most likely to get wrong. Sorry about the noise. Okay, let's have a go. In fact, no, we've got properties. So alkenes, what are they like? Well, actually, there's quite a lot more fun chemistry to do on this in the next topic, which is the organic reactions topic. But in summary, the alkenes, like the alkanes, are fantastic fuels. In fact, they're even better than the alkanes, because those losing 2 hydrogens makes them slightly wonkier shapes, and so they're not quite so good at sticking to each other. Their intermolecular forces are just slightly weaker than the equivalent alkane. So for any alkene, it's just slightly more volatile, and therefore slightly more flammable than the equivalent alkane. And they're also slightly less viscous. You can see this really easily at room temperature by looking at hydrogenated, which is basically manufactured to be alkane, fats, let's say margarine, and vegetable oil, which is the unhydrogenated alkene version, which has multiple double bonds in its chains. So the fundamental difference is, one has got double bonds and is a liquid, one does not have those double bonds anymore and is now a solid. And so that's a really nice example of having that higher melting and boiling point if you are a saturated hydrocarbon, because you tessellate better, and so you stick to your neighbours better. They have slightly stronger intermolecular forces. So they're better alkanes at being fuels. Fair enough. They're also better alkanes at doing really anything else. And the key thing is that double bond. We call that a functional group. So all of organic chemistry is built around the principle of having long alkane chains with something in them that does something. And that thing that does something is a functional group. And in the case of an alkene, that functional group is the double bond. And it can do a variety of interesting things. They are a region of high electron density. There are 4 electrons between 2 carbon atoms. That's a lot of electrons for a carbon atom area. And so that region is electron dense. That means that things called electrophiles, I know, hilarious name, it is derived from exactly the same source of paedophile, because it means the phile just means lover, and the electro in this case means electrons. Pedo in the case of the other word means child. There, of course, in chemistry there aren't just electrophiles, there are nucleophiles, which like nucleuses and therefore positive charge, but in this case we're looking at a double bond with lots of electrons, so the things are electrophiles. This is an A-level word again. I do not expect you to need to know electrophile at GCSE, but it does kind of explain things that otherwise are seem more like magic than science. So let's stick with mentioning it and don't learn it if you don't want to. And these then carry out what are called addition reactions, where things that want electrons come and attach to that double bond. And you can do all kinds of cool things with these alkenes by adding fun things onto them. You can make very, very useful things. And one of the most useful is you can make them add to each other and make polymers, like the clothes you're almost certainly wearing now. Again, sorry about the background noise. Okay, moving on. This is my challenge for you. I'm not doing the test for alkenes today. I'll let Madam do that when you do cracking, or actually probably me. I'll do that when we do cracking, because the natural process is how do you make alkenes, followed by how do you test for them. But what we will do is I would like you to summarize, please, the names, formulas, and just for a bit of calculation practice, the relative atomic masses, or relative molecular masses, now let's call it formula mass, of all of the hydrocarbons that we have met today, the alkanes and the alkenes. If you want to carry on past 5, go for it. You may have to Google numbers bigger than 10, because actually after pentane it's the normal names for number of sides of shapes. So pent, hex, hep, oct, non, and dec all work fine, and I just haven't ever bothered about learning the ones above 10 properly. So if you want to do silly things, go and look up dodec and stuff to work out what the names for alkanes with really long chains would be. But the bit I care about, of course, is up to 5, because up to 4 of alkanes is on your specification, and up to 5 alkenes on your specification. Just you don't do methene. So really, whilst this is officially not on your specification, there's absolutely no reason in the world why I couldn't reference to pentane, because you have to do pentene, and so it's completely ridiculous that you don't have to learn why you have to learn pentane. So just learn pentane. I mean, how hard is it? Okay, so have a go at filling that all in. I suggest you pause and spend a good bit of time doing that. I will see if Madam can send that to you, or if I can send it as a Word document or a PowerPoint alongside it, so you can just print it off if you want to. And yes, hopefully my clear introduction, my slightly rambling introduction to alkenes and alkanes has left you wanting more and loving chemistry, because that is all I can ever ask of you. Meanwhile, I'll just say it's a real pleasure to, I use the term meet advisedly, it's a real pleasure to say hello to you all. I'm rather sad it's been a rather one-sided conversation, and please email me any questions, any queries you want about alkanes and alkenes, and if there's something you'd like explaining in more detail, just send it to me and I will either type it back if I can, or I'll make another video and send that as well. I've thoroughly enjoyed this one. I know I went on a little bit, I've been a bit wordy, but getting these right is incredibly useful, and if you can learn these and get them right consistently, that's many, 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 many marks. Just a little bit of an in-joke. That's the summary sheet, yeah, animating up the title, helpful. Right, a little bit of an in-joke is if you complete that task, there's a prize. The prize is cake, And of course, the in-joke based on the theme of the PowerPoint is the cake is a lie, for those who haven't got the popular culture reference yet. Okay, if you are doing the task, pause the video now because I'm about to show all the answers. Answers. So, I left a gap for the CH4 formula for methane, and I gave you the relative mass of 16, but there's a display formula drawing. These two-dimensional display formulae are the way you'll be asked to draw these molecules. You'll not be asked to draw them in 3 dimensions. That's, again, an A-level thing. So the names were methane, ethane, propane, butane, pentane, CH4, C2H6, C3H8, C4H10, C5H12. And there are the drawings. I can't really say those out loud. And the relative mass 16, 30, 44, 58, 72. Each time you add 14, which makes complete sense because each time you're adding a carbon, mass 12, and 2 hydrogens, mass 1 each. So each time you're adding 14. Let's have a look at the alkenes. We've got ethene, propene, butene, and pentene. Formula C2H4, C3H6, C4H8, C5H10, and display formulas as drawn there. Remember, I said you could put those double bonds wherever you like in the chain. I just recommend putting them at the end because it's easiest, and you're less likely to forget that this carbon does not have a hydrogen. That vitally important feature. Go on, be honest, how many of you put hydrogens on that double bonded carbon? Also, it's worth mentioning that in display formula, it doesn't matter about the angle at the end here. I showed you the drawing earlier with the double bond having 2 angled hydrogens off it. That's, in terms of 3-dimensional chemistry, more correct, but we just don't care at GCSE. We're not showing 3-dimensional structure, so the correct bond angles are immaterial, and we tend to draw them in a straight line, basically for convenience. No really good reason for it other than it's easier. Okay, masses, 28, 42, 56, 70. Please tell me if I've got any of those wrong. I'm pretty sure I've just added 14 each time, which is exactly the right thing to do, but, you know, it's somewhat hard to concentrate when small people are around, so there may be errors. I will definitely put a pride on if anyone finds mistakes.